Okay. Can you guys hear me?
Yes, we can hear you.
So, my computer plugged in. I was thinking before we move on, maybe we should try to look at just a silly example, just to see how these things might look in a specific example. And okay, so let me switch over to my document camera and just write a little bit. Right, so let's do so. Let's consider. Right, so I use MATLAB and Mathematica. So you need to use C++ as we talked about. But I'm going to be using MATLAB and Mathematica today. And the simple example I want to consider is just you take a uniform. This is a uniform on 0, 1. And I just want to calculate like the expectation of, say, e to the u. Right, so this is very easy to do analytically. Right, you can write this here as an integral over the codomain 0 to 1, e to the little u, and then it's uniform, so it's just du. Right, so this here becomes, what does it become? E to the 1 minus 1. Right, but what we're interested in is trying to use this for, how to calculate this value on the right-hand side, or approximate it by using simulation. So what we're going to do is we're going to generate UN. We're going to generate UNs, and then we're going to be looking at the average. So that will be e to the UN, sum them, and take the average. That's going to be our approximation for e to the 1 minus 1. And we're going to be looking at confidence intervals. So let me try to show you how one could do that in this simple example here. And I'm going to use, for that part, I'm going to use MATLAB. So I have a little script here. If you're not used to looking at MATLAB, the reason I'm using it is because it's very easy to write code in. Right, so this is my function, I'll just call it test. The first thing I do is I pull uniforms. So let me just delete all these. So my U here, the command that MATLAB uses to generate uniforms is this rand, R-A-N-D. This here gives me uniforms. This creates realizations of this capital U. So in here, this is going to be the number of points that I'm interested in. So I'll go over into Mathematica, and I'll call my function, which I call test, and say I want tests with like 10 values. It's going to give me this these 10 values of a uniform, 10 realizations of the random variable u, which is uniform on 0, 1. Right, so those are my u's, and I could have more, right? If I wanted 100, I'll just put 100 here, and it'll give me a bunch more. But let's just stick to a smaller number so we can have it on the screen. So 10 uniforms, and you can see every time I call it, I'm going to get different values. If you don't like that, there is a way around it. And I think the way around it is to use a command called seed. So we can, I don't want to do that, but if you don't like that every time you call it, you're going to get new values, you can see how they change every time you call it. There will be a way to get around this. So you seed your code, so it will give you the same numbers every time you run it, and this might be helpful for like debugging. I'm okay with getting different numbers every time I run it. So I have a vector u, and this is uniform, right? And so the first order of business is to transform these values into exponentials, right? Because that's the thing I want to approximate. So I'll be able to do that simply by plugging it into x. So when I plug it into x, now I'm going to get these 10 values exponentiated. So you can see you're not going to become bigger than 1, right? Because all the values are positive. So these ones here are my exponentiateds. And then what I want to do is I want to take the average, because this is what I'm interested in. I'm interested in taking the average. Okay, so I'll take the average. You can either do that by, in the case of Mathematica, there is an operator that's just called mean. If you don't want to do that, you'll have to recode it, and you can do something like for I forget how it is. Is it I 1 to 10? Of course, I forgot what the commands are like. So go to MATLAB, and then you do for loops. How did it look like? So this is how they look like for something, and then you need to put an end at the end. So I'll do that. So for if I'm counting from 1 to n, I'll have to take the average. So I'll set a to be 0, and then I'll take a plus a equals a plus, and then I'll exponentiate u of the value, and I'll end it, and then I'll report a divided by n. So now I can either use MATLAB's built-in mean, or I can create my own little mean average thing here, and hopefully I'll get the same. And of course I have to get it printed out, so drop the semicolon. And you see I get indeed the same value. Right, so that's my estimate of this integral e to the 1 minus 1. Right. Took these numbers and I took the average. The first one, the mu here, this is when I'm just using the built-in command, and the second one is when I build my own for loop. One thing MATLAB has going for it is it is always much better to use the built-in commands, because you run faster. It uses this vectorization idea, and my for loops here, they're not nearly as fast as MATLAB's built-in commands. So that's, and then I need to get my hand on the confidence interval. So I need the standard deviation. Okay, so let me just eliminate this for loop. I need to compute the standard deviation, and again, just as the mean has a built-in command, the standard deviation has a built-in command. So I can do that. So that will give me now, and of course I have to drop the semicolon. So one is printed. So here's the here are the values, here's the mean, and here's the standard deviation. And so finally, to get the confidence interval, we use the formula we had before. The confidence interval, the endpoints is this 1.96. Then I do the standard deviation, the empirical standard deviation that I got out from the data, and then I divide by square root of n. And you can see here, I'm using 1.96. I'm not going in and using this these t values that we talked about. I'm happy enough at 1.96, even though n is only 10 here. And so when I go ahead and print it out, I'll get these endpoints. So you'll need to report these confidence intervals. Like, so this is mu plus minus this value of 3.56. And of course, now I can, this was done just with 10 points, and I can increase this. Let me just, I'm going to eliminate the printing out of the U, because otherwise it's just going to get too wild. So just going to get rid of the printing there. So I store the realizations, I compute the mean, compute the standard deviation, and then I form this confidence interval. And if I increase this now to, say, 1,000, you can see the confidence interval shrinks quite a bit. It goes from 0.3 down to 0.03. Well, that's because it decays with root n. And of course, I can go up to more realistic values, like with 1 million. And you can see now the mu that you're interested in. This is 1.7188. And if you are to compare it with the true one, this was x of 1, right, minus 1. Right? So this is, the value is 1.7183. And I'm now looking at 1.7188. So it's getting closer. We have a standard deviation, and then we have the confidence interval. And this is for 1 million sample points. Are there any questions on this? Of course, this example here is, the relevance of it is just to get some practice on how to use simulation. It's of course silly from the perspective of doing calculations, because this x plus 1 minus 1, I mean, this is easily calculated. Are there any questions on this part? This is just a little example to show you how the formulas that we've been deriving, how they look. And when you're up here with 1 million, and then you start looking at confidence intervals, it makes absolutely no difference if you use 1.96 or if you use these t values. They are the same for all practical purposes when you have such a large sample size. Any questions? So while we add this example, there are like tricks that you can play to make this even better. And let me just try to show you. Let me try to show you one trick that you can play. So as you can guess here, it's all about getting this sample standard deviation lower, right? Because the lower the standard deviation, is, the better your confidence intervals are, right? So there are many ways to improve or narrow the confidence intervals. There are many ways to narrow confidence intervals. Called these are called variance reduction techniques. And here's one. The one we're going to be looking at. So here's an example of what's called an antithetic variables. So this is just one of them. There'll be more coming, maybe not today, but then next week and in the homework. Right. So the observation that the trick that we're gonna use is almost embarrassing simple. It simply just goes by, so to just note that if U is uniform, so if U is uniform, well then so is minus U. Okay, right, so if we go back to the example, so you have a uniform, you take the minus of it, so it's a uniform on 0 and 1. I shouldn't say minus 1, I should say 1 minus U, right? If U is uniform 0 and 1, then so is 1 minus U. So if you go back to the example where we want to calculate, what was it? It was e to the u. So we want to calculate this e to the u by approximating it with, if we want to approximate it with this 1 over n, and then the sums of e to the un. Right, there are alternatives to this, which are alternatively, well, what we could do is we could use that if I take the expectation of e to the u plus e to the 1 minus u divided by 2, like this is still going to give me the expectation of e to the u, right? Because the distribution of u and 1 minus u is the same, so the expectation then is linear, right? So I take the average of these two, I'm just still going to get that thing. But the cool thing is that the variance of this random variable e to the u plus e to the 1 minus u divided by 2, this is probably, this is much smaller, can be, I should not say always, but often is smaller than the variance of this e to the u. Right, so let me try to show you how to do that. So be interested in figuring these two things out. Okay, let's go and show you how one could go about studying that. And let me use for actual simulation, I like to use MATLAB. For these analytic calculations, I like to use Mathematica. So let me show you here how to use Mathematica to say something about this. I had a little script somewhere. So this is my Mathematica script. This is my Mathematica script. So the first moment, I'm going to be integrating. So I'll integrate the exponential. Let me call this one here for little u. I'll integrate the exponential from 0 to 1. Like that was that value. That was that value we had before. And now my code doesn't want to run. I don't really know why it won't run. Try this again. Will you run now? Now it'll run. Okay, so that was that value we were trying to simulate before. So remember what it was. It was x of 1 minus 1. So the value we're trying to get at numerically is this value we had up here. That was the one we were simulating over in MATLAB before. All right, so the first moment is this thing, and then I'm interested in the second moment. So let me get the second moment out. So the second moment, how will I get that? Well, I'll have the second moment would be, I'm going to integrate this thing, but now I'm going to put a square in there. So I'm going to be integrating here. It'll be 2u. That'll be my second moment. And then if I want to get the variance, this here will give me the variance to be variance would be what? It'll be the second moment minus the first moment. So 2 minus the first moment squared. And it'll be that value. So that's the variance I'm looking at without doing any tricks. 0.2420. So now we get creative and we want to reduce the variance. Okay, so how are we going to reduce the variance? Well, the proposal was to look at instead of this M2, we would use a different one. We would look at a different estimator. We would look at M1 being this guy. We would look at M1 being E of u and then plus exponential of 1 minus u divided by 2. And of course, this is going to give us exactly the same first moment, right? Because both the integral of x of u and u is uniform 0, 1, so this is going to give me exactly the same value as the one I had to begin with. But the difference is going to be that when I compute the second moment, I'm potentially going to get something here that is quite different. So I'll have to integrate to get the second moment out. So let's just write that on a piece of paper to make sure we get it right. I'm looking at, like that was what we just saw, right? But I'm also interested in the variance. So I'll have to compute the second moment. So to get the variance of this object, EU plus e to the 1 minus u divided by 2. So I'll have to compute the second moment of it. This would be e of, and then this thing squared. So it would be e u plus e to the 1 minus u divided by 2, everything is squared, and then minus the first moment squared. So the first moment would be, we already had that one, that was just the expectation. of e to the u squared. So let's try to look at how this variance changes. And of course, the point being that this variance here is going to be different, and it's going to be much smaller than just the variance of e to the u. Okay, so let's try to do that. So we'll have to integrate this thing here squared, and then we have to compute the variance. And you can see here that when I'm computing the variance, I'm going to get 0.004. And the other variance is up here. The difference between these two numbers is humongous. Right? This number up here, the primitive just brute force, it is much, much bigger than when I play this trick between u and 1 minus u. So this variance here is much smaller. It's going to give me a much more precise estimate when I perform simulation, where I do this trick with e of u plus exponential of 1 minus u divided by 2. So if you switch over to MATLAB and make that adjustment, let's see how that goes. Where's my code? All right, so now we're back over here. The code, the change in the code is minuscule. Instead of computing the mean of e to the u, I just perform a little change here in saying that this is just 1 minus u here, and then I take divide by 2. You can divide by 2 inside if we so desire. And then I go down to the standard deviation. This is going to be the same. I'll have to compute the standard deviation of the number I have down here. And then I run it. And what did I run it with? This was the confidence interval. This was the size I had with the primitive 1 million samples. So now I'll run it with this upgraded world. And the improvement that we're seeing, you can see it here. It is not the same. There's an improvement. And indeed, you see it in the standard deviation, when it goes from being this 0.5 down to being 0.06. The standard deviation is much better. Of course, the means are similar. So what this trick allows us to do is it reduces the variance, and thereby it increases the precision of the estimate. Questions on this? There are a couple of places where this often comes up. So you often see it. You often see this. This trick used for these uniforms. So we have U uniform. Let's say 0, 1. And that's going to imply that you have this uniformity. This is also uniform. That was the one we just had. So that's one you see a lot. The other one that you also see a lot is if you have x standard normal, if x is standard normal, then minus x is also standard normal. So you see this, these two settings here. You have a uniform or you have a standard normal. You'll see this trick being used. So for example, an example of the latter, so an example of 2, and this is also going to be in your homework. When you look at the Bachelet model, so your x up here is standard normal. So here you have a k minus x positive part. That's the Bachelet model. And then you also have the Black-Scholes. Excuse me. I have the Black-Scholes model. This is where we're interested in calculating k minus, and then there's an exponential in here. So then in the Bachelet model, you would use so instead of using what would we do? We would have your xn's, right, and then there would be a minus and then a k positive part. Take the average. So instead of using this in the Bachelet model, you could use, what could you do? You could use so you could use the expectation of k minus x positive part, well, is going to be equal to, and then there's an expectation, and then you have a half, and then you'll have k minus x positive part plus, and then you'll have k, and then you replace x with minus x, and you get the sign change. So you could do this. You can use a distance property, and then you could estimate using 1 over n, and then the sum, right? And then you sample in here. So this is going to be 1 over 2 k minus xn positive part plus k plus xn positive part. And the point being that the variance of this quantity here is typically much smaller than the variance of this quantity. And something similar, of course, can be done for the Black-Scholes model. Likewise, Scholes model, instead of using 1 over n, and then the sum, and here we have k minus e to the what, xn. this, you could use 1 over n, and then the sum 1/2. What would it be? It'll be k minus e to the xn, positive part, plus k minus e to the minus xn, positive part, with the hope that the empirical standard deviation of the second term would be smaller than on the first one. Are there any questions or comments on this part?
So what's the magic behind this trick?
Yeah, so when does this work? So when does that work? So when does this trick work? So the question is, well, we're looking at so let's look at the uniform case. So let us consider the uniform case. So we're looking at an expectation of g of u, and we're looking at the variance of g of u, and we're comparing this. This is the simple way, and then we have the antithetic case. So here we're looking at the expectation of 1/2 g of u plus g of, this is the uniform on, say, 0, 1, of g of 1 minus u. And then the variance of 1/2 g of u plus g of 1 minus u. And we already argued that linearity of expectation will give us that these ones are the same. So what it comes down to is comparing these two. So when do we have that the variance dominates, and preferably is much bigger than the variance of 1/2 g of u plus g of 1 minus u? When do we have stuff like that? Any ideas? Like, we absolutely do not want the opposite, right? This is what we want. We really want this to be much bigger. This is what we desire. So what properties on G would give us something like this?
The covariance of GU and the G1 minus U is small.
So that's the point. Yeah. That's the point. We can make this a little bit better, right? Because the variance is equal to this second moment minus the first moment squared, but we already argued that the first moments are the same. So in our particular case, this is the same thing as arguing that this is the second moment has to be much bigger. And of course, this is what we desire. Messed up the parentheses here. This should not be there. So it's going to be something with the covariance between G applied to U and G applied to 1 minus U. You can also try to play here with convexity. There's probably going to be something with Jensen's inequality, right? Because 1/2 U plus 1/2 1 minus U, there should be something with convexity. So it depends on G's properties. And indeed, you do not always have this. You don't always have that this trick here works. A very good question. Okay, so we're almost out of time. There's like one last thing and this is something that most of you probably already know, but let's just recall it because for simulation purposes, this is quite important. Like the starting point we had was that we could generate uniforms. Like that was all the way on one of the very first slides. Right, that was on one of the very first slides. So I did. The starting point was that we could generate uniforms. And now here, for example, at the last on the last slides, we were talking about normals. So how do we go from normal? How do we go to normals from uniforms? So this is just this is what's called the probability integral transform. So how do we get, for example, normals from uniforms? We can, this is what we were given to sample, but how do we turn them into normals? Well, so just most, if not all, software can give you normals directly. So let me just show you how one can do that in MATLAB, because we just looked at it and it's a very simple change. Let me share my screen and then just show you the one-line change that you have to do. So here was the code we were running, and so we have the command U is equal to rand. So there's that word rand here, and so instead of rand, we would want to have we want to have standard normals, well, we need to figure out what is the different command that you have to put here. And so just Google it, MATLAB normals. And you see it here, this is norm RND. The thing to look out for, and this is why I wanted to bring it up, is inside the syntax, when you call this norm, you'll find mu and then sigma. Sometimes it's sigma squared, and sometimes it's sigma. So here it says it generates a random number from the normal distribution with mean, mu, and standard deviation. Okay, so that's important because if you are to generate a non-standard normal random variable, then the variance matters. Okay, so the code is mu and sigma, and then however many you want of them. Okay, so let's go back and try to plug that in here. So it was norm R and D. Mu is 0, sigma is 1, and I want a vector. I want a vector of them, and then you just go back to the code. Let's just run it with 10. And then now it'll spit out, if I print out these, that was the wrong one. There we go. If I print them out, we can see them. Like before, they were numbers between 0 and 1, and now they're going to be standard normals. So they're going to be all over R. And you can see that they are both positive and negative. They have mean 0 and standard deviation 1 or variance 1. I wanted to point out and look out for this variance. It depends on what software you're using, what package you're using. Sometimes it's the standard deviation in there, and sometimes it's the variance. When you see me write that second entry that's inside N, and you see that, and let me just highlight this. Like that variable here, this one here, for me, this is the variance. But for many software programs, that second entry here is the standard deviation. Okay, so that's just a thing to note. So many software packages, if not all, can give you these normals directly, and they can give you many other distributions directly. But this probability integral transform, it actually allows you to go from normals to any other distribution that you want. And I'm sure many of you have seen this before, but for those of you that have not, there is this trick that will say, like, so say X's distribution is F. Right, so what that means is that I look at the probability that the random variable is less than some value X. This is my F of X. X is in R, right? That's my distribution function. So let's start by saying that say F is strictly increasing. So there are no flat spots. Then the way that you would go about it is to say, well, okay, so let me take a U, and I'm going to take U to be F composed with a random variable X. And let me compute what that random variable is distributed as. So that'll be P of U less than little u. And this is obviously a number between 0 and 1, because F is a distribution function. So that number here is between 0 and 1. And we'll get P of F of X less than U. Right, and now comes a time when I'm using that it is strictly increasing, so I can move this F to the other side. and I'll get P of X less than F minus 1 of U. And then I'll have what I want, because X had distribution F, so this here will be F of F minus 1 of U, which is U, right? So that random variable U here, is uniform, right? So I can simulate U's. Okay, so we can simulate. UN. So that would be F of xn's. And then you just invert. This if we just invert, we get F minus 1 of UN. This would be my xn's. So if I can get my hands on the uniforms, I plug them into the inverse distribution function, and it's going to give me realizations of any distribution. The only little problem is I need this strictly increasing property, so that rules out a bunch of distributions. Right? I cannot have this. This rules out if I have a distribution function. So I'll have something, and then if there's a flat spot, in here, it doesn't work, because how would I do the inverse? This would be difficult, because the inverse would have a vertical line, and those are not functions. So more generally, so in general, if F has these flat spots, you can use this generalized F inverse of U, because that's the one we need up here to get my x's, F inverse. You can use this one here. This is the smallest. This is the smallest x, such that F of x is bigger than U. And then this one here works. Okay, this I think it's a good time to call it quits for today. The next topic is this acceptance rejections algorithm, and this is a pretty big chunk of text, and we're almost out of time, so I don't want to do that now. Let me start by asking if there are any questions. Are there any questions? There are no questions, and I just want to remind everybody that their office hours tomorrow morning, and the office hours tonight and tomorrow night with a TA. Oh, Alice has a question. Yeah, so Alice is asking the infimum part. Yeah, so the debate is if you have, yeah, we can try that. The debate is that the debate is if I have a distribution function that looks like this. Well, I need to switch over so you can see what I'm writing. Otherwise it won't work. Like if I have a distribution function that looks like, say, this. And this is my f. So I'm on to do the inverse, right? I need to do the inverse. I need to mirror. I want to mirror in this 45-degree line. This is my 45-degree line. want to mirror this thing. So ideally, what I would do is I would have like this thing here is going to get mirrored. It's going to get mirrored up to here. And then it goes up here. Like, so my inverse function is going to be, so it go like that, go up here, and go like that. That would be my F inverse. But that won't work, right? Because this is not a function. This is not a function because it has this horizontal piece. That's not a function. So what this infimum up here allows you to do is, well, the problematic part is this one here. And so what do you need to settle on? So this here is this is not a function, so it won't work. But what you can get to work is if you just look at all the nice places. So that's going to be this one, and then this one. And then what you need to settle on is where do you want to put the value, upstairs or downstairs? Do you want to put it up here, or do you want to put it down here? And I think this one here settles on, you should do this. And this one here is okay. That's a function. So that's all that formula does. It chooses one of these endpoints. Good. Okay. So again, about the office hours. So the TA has office hours on Thursday and Friday nights. I'll have them on Friday morning, and I'll hang around for a while. But if nobody shows up, I might move on and do something else. So try to be there in the beginning if you have questions. Okay, I'll post these handwritten notes, and then the videos are going to go on YouTube, and there'll be links provided on Canvas for these things. Any other questions or comments? Otherwise, I'll see you guys next Thursday. Okay, have a good weekend, guys, if I don't see you tomorrow. You're welcome, guys. You're welcome.